This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Can anyone tell me why you usually choose more than one capacitor? Yes?
You can pick like a bulk capacitor, which is usually slow to react,
Yes.
and then something that's a bit smaller that's quicker to react.
Sure, exactly, right? So therefore you've got various capacitors with various ESRs or ESLs, right? Equivalent series inductance or equivalent series resistance, right? So therefore you usually choose the right ones in order to do that. And usually, even though electrolytics, as an example, might have a lot of charge, they respond very slowly, whereas you might choose, ceramic or paper-based or other types which actually have a much faster response, so you can actually get the charge out of them very, very quickly. So a capacitor is not, essentially what I'm saying is a capacitor is not a capacitor, right? So you've got to choose the right component for the job, right? That's why there's data sheets with lots of capacitors, various types of, with not only capacitance values, but also each material or construction actually has certain advantages and disadvantages. Right. So generally, if you're trying to do decoupling caps, usually go for a ceramic or I think it's polypropylene thin film type of capacitors. Right. So you can actually you don't get a lot of charge, but they respond very, very quickly. All right. Learned something, hopefully something useful. Which isn't exactly on the course, but anyway, nonetheless, something that you might find useful when you're out there working as engineers. So, in the last lecture, we briefly started to talk about Smith charts, right? And what we did is we went through the derivation of the Smith chart. I won't spend too much time on that, other than to say, yeah, we went through a derivation and that's great, but not necessarily. I'm not going to on the exam or on the at some stage on the test. I'm not going to actually ask you to derive a Smith chart. I don't particularly care if you know or you don't know how to derive a Smith chart. What's important is that you know how to use a Smith chart, right? And specifically, the use of a Smith chart or where a Smith chart has utility is essentially in allowing you to solve some complex problems as it relates to impedance. So it's a convenient graphical tool in order to manipulate impedances and work with impedance values, right? And then what we did was we looked at some examples. We looked at the simplest one, which was here where it was. We had a transmission line with a characteristic impedance, and then we were connecting up to some load, and we said, well, this is connected, the load is connected to a transmission line of length, of the nature of the wavelength. What is its input impedance? And just for everyone's benefit, just so that we don't leave anyone behind, what I'll do is just go quickly through this and then we'll continue on with some of the other examples. Essentially what I said was, well, the first step was, if you know the characteristic impedance, work out the normalized impedance, and we worked out that point on the Smith chart. Oh, geez. Doi. Okay, thank you. And it's washed out for some reason. I tried using this one, but this one was... Anyway, if I do this, is it any better? No, but then you guys get blind, right? How about, is that almost acceptable? It's fine? Okay. All right, let me just move so it doesn't blind me. So what I said was, in order to solve that specific problem using the Smith chart, and I'm hoping that you've all seen the Smith chart. I can see some faces that weren't here in the last lecture, so I don't know if you've actually gone through the lecture notes, but I'll I'll go through this particular example again. I said, well, one of the steps in order to be able to use this Smith chart was essentially draw on the Smith chart the normalized impedance. Then I said use this extremely dangerous but very useful piece of equipment, which is a compass, in order to work out your voltage standing wave ratio circle. So essentially put it at the origin and connect it up to the point, to the impedance point, draw the voltage standing wave ratio circle. So therefore that voltage standing wave ratio circle dictates all the impedances that you would expect to see for that load, if it was connected through a transmission line with characteristic impedance of Z0. Right, so that gave you your voltage standing wave ratio curve, which also corresponds to all the values of possible impedance. And one of the things that we did say was, if you wanted to work out what the voltage standing wave ratio was, you just measure, the radius, and you go down here, and you can work out that the voltage standing wave ratio is going to be roughly, 3 to 1, right? So there's a couple of things down here on the on your Smith chart. Then what we said was, I wanted essentially to work out what the impedance is going to look like if I'm connected through, this transmission line on lambda on 8. So what we say is we want, what does the impedance look like if I'm going towards the generator, right? Because I'm going in that location. Sorry, I had it here and I rubbed it off. If I'm going towards the generator, what's the input impedance going to look like? So essentially, I've got to calculate what lambda on 8 is. Lambda on 8 is 0.125 lambda. So essentially what I do is from this point, I draw, this location on the Smith chart, and from this point, I move 0.125 towards the generator. 0.125 lambda towards the generator. Right. And then what I do is I draw the line through this point, from this point to the origin, and the location at which it cuts or intersects the voltage standing wave ratio circle is what the characteristic impedance is. Oh, sorry, what the impedance, the input impedance of that section, that load with a lambda on 8 transmission line connected to it. Now, I'd mentioned this at the previous lecture. I'd made a slight mistake on the notes. I'd actually put this as positive rather than negative. It's actually negative, so it's 2 minus 1 omega. So that's the input impedance. Now, in one of the other examples we went through, and I just want to ask, what's the minimum impedance and what's the maximum impedance that we would expect in this configuration? And I'm not talking about, if I had an arbitrary length of line, right, not lambda on 8, what's the minimum and maximum impedance that I would expect for this setup? It was an example, right? We did it, yes?
Consider on the horizontal line, like
right.
at the very bottom.
Right. So if you remember example 2, what we went through and said was, if we wanted to work out the maximum impedance, it's essentially this location here, right? That's the maximum impedance, and if we're reading off the constant R circles, it will be 22, 24, 20, roughly 26 to 27 ohms, or 27 ohms, but we have to multiply by the characteristic impedance. So 27 by 50 is 1,350 ohms, roughly, I think. 27 times 50. Yeah, 1,350 ohms. And the minimum impedance is where it hits the line with x equal being 0, and it's roughly 0.4, so it's 20 ohms, right? So essentially what the Smith chart is allowing us to do is to actually work out not only what the not only what the impedance is for a particular length of line, but it also allows us to calculate voltage standing wave ratio. It allows us to work out the minimum and also maximum impedance. And as you know, and not to go through example number 2, one of the things that you know, if I asked you specifically, like in example 2, what length of line gives you the maximum impedance? Can anyone tell me? All right, so we're going from here to here, right? So what was the value here? So it's 0.16 lambda. So 0.16 lambda is going to give you your maximum impedance, right? What length of line is going to give you the minimum impedance? So I'm going to go all the way from 0.16 plus 0.25. So 0.41 lambda is going to give me my minimum impedance for this particular configuration. Right? So it gives you a lot of useful information, right? And it allows you to do it in a graphical way. And in addition to that, it also allows you a convenient way to plot impedances, right? At the moment, we're plotting impedance and we're doing nice circles, but usually when you have losses or you have active devices, you know, the circle, the constant voltage standing wave ratio circle, you don't have a nice circle, right, for impedance. The impedance actually changes. You can actually get loops which, you know, indicate resonances and things like that. And that's why, you know, on a vector network analyzer, the impedance or the characteristic impedance or this, you know, S11 and the like are actually plotted, or S11, S21, or all the scattering parameters are actually plotted on a Smith chart. So you've all used the VNA? Vector Network Analyzer? Yeah. Yes. I've been told that you've been that in your tutorials or workshops that was one of my tutorials, that actually to get you to use a Vector Network Analyzer. Maybe it's coming up this week. Okay, well, at least this way you'll know what you're looking at on the Vector Network Analyzer. All right, so we'll do another example. We'll do another 2 examples before we do the design of matching networks. I've gone through this and I'll go through this again. So let's go through this step by step. And can people please give me the information, because otherwise I feel like I'm just, you know, reading it out or, you know, not getting the feedback. Right. Okay. So let me hide this. But you've all got the notes, so I guess you can easily just look at the notes. It doesn't really help. But so suppose you had a 50 ohm transmission line. You can't see. Sorry, what do I do? Just zoom in. Okay. All right. Hopefully that works. Where's the little... Yeah, okay, maybe that's better. Okay, so we've got a 50 ohm transmission line, and it's terminated with a load of, which is 15 plus 10J ohms. And then I ask, I've got a shunt open stub, which is located at a distance, in this particular case 0.44 lambda from the load, and has a length of 0.147 lambda. And then I'm asking you to calculate the impedance. Can people tell me the steps? And don't just read it out. I mean, just explain to me the intuition, right? Because I can read too, right? And I actually write the notes. So, all right, so what's the first step? Why? Perfect. All right. Good. All right. So you've done that. Excellent. So we found the point on the Smith chart. All right. And what we're saying is it's 0.3 plus 0.02J. So 0.3 and 0.02J. So we have to find, you know, positive 0.2 and 0.3, and we draw the point. Excellent. Then what do we do? Well, well, I'll give you a hint. We'll just draw the voltage standing wave ratio circle, right? So let's draw the circle. Let's pretend that we're doing this for the first time. We draw the voltage standing wave ratio circle. Question, what's the minimum and maximum impedance in this particular case? It's not part of the question, but let me ask. What's the minimum and maximum impedance? It's really hard to say. I apologise. All right, for anyone that's got the notes, so it's, all right, so we said the minimum occurs at this point, and it's 0.3, right? So what's the minimum impedance? 15 ohms, excellent. All right, what's the maximum impedance? Yeah, around 3.4. So 3.4 times 50, which is 170 ohms. Perfect. All right, so we know what the minimum and maximum impedance is. What's our voltage standing wave ratio if I'd asked you for that? Perfect. All right, okay. Done. So we said it's here. So we'll work it out here, and it's roughly 3.6. Okay. Let me ask a different question. What happens if I asked you, using the Smith chart, tell me what the admittance of that load is? How would you do that? Yes. All right. So you remember it was we go to the opposite side of the circle through the origin, right? And I apologise. I should have brought a ruler with me. And we would have just it's diametrically opposite, so that would have been the admittance here, roughly. Right, somewhere around there. And as I said, I almost failed first year engineering drawing, so don't ask me to really be drawing things. But it would be roughly, did I draw it correctly? So it's just diametrically opposite, right? So it's, yeah, so roughly there. So that is what, 10, so 2, 4, 2.2, 2.4, 2.2, so roughly 2.3, and roughly 1.6 J, right? So remember, that's how you calculate from admittance, from resistance to admittance. You just flip on through the centre of the Smith chart, you know, the 1, 0 point until you hit, you know, the opposite line.
Should it be negative 1.6?
Yes. Yes. Negative 1.6. Yes. Did I say positive? Yes. I'm sorry. But below this line's negative, above is positive. Thank you. Yes. Okay. All right. So we've calculated the admittance, but the question never asked for that. I was just asking you. Okay. We said that this load was connected via a transmission line which was of length 0.44 lambda. So what do I do? Clockwise, yes. On here, so I am at this location, so I've got to find 0.44. So essentially start from there, add 0.44, and this is now my location. This is the actual impedance, the input impedance at this location now, right? Because all I've done is I'm going towards the generator, and the length of the transmission line is 0.44 lambda. So what I do is I start from here and move towards the generator and look on the outer perimeter of this Smith chart and add and move 0.44 lambda, right? So it was roughly a point, what is it, 0.34, I think, and I have to go to and I have to add 0.44, so it's 0.74, right? And that's where I'm at. Okay, I asked you, then I said I'm going to add a shunt stub, right? So if I'm adding a shunt, what do we do to add impedances in parallel? We use admittances, right? So what we have to do is I'm going to convert this resistance to an admittance. So what do? Flip across the to this location, right? So it was go through the origin, flip to this location. So I know my impedance there, right? And I can read that. And my impedance, you see this time I got it right, is Y equals 1 plus 1.33J. Essentially, I'm on this line and I'm looking at roughly where's this point into, where's this point? And it's roughly 1.33. All right, excellent. Now I'm going to add a shunt open circuit line of length 0.147 lambda. What do I need to do? I've got to work out, the first step that I've got to do is actually work out what is the input impedance, input admittance, or what is the admittance of a line, an open circuit line of length 0.147. How do I do that? Using the Smith chart. Well, so what do we know about an open circuit line that was of zero length, but and it was open circuit? What's its admittance? Zero. Okay, because its impedance is infinite, right? So if I was infinite and I'm flipping around, I'll go to zero, right? That's easy. That's another simple way of determining that. Okay, and I said now that, what's my length? 0.147. I'm starting at this location, and I'm going to move around until I hit 0.147. And essentially all I'm doing is looking at this location on the Smith chart. It's 0.147, and so what we see is the admittance is positive 1.33 ohms. Okay, if I'm here and I'm 1 minus 1.33, and I'm going to add 1.33, where am I going to end up? So essentially I'm moving along a circle of constant resistance. I'm only adding reactance, right? Positive reactance. So essentially I'm just moving along this line. So I'm going from minus 0.133 and plus 1.33. I get to the origin. So what have I done? I've done a perfect impedance match, right? Now, that's what we're going to do supposed to be doing in this lecture, but I just wanted to make sure that you're all familiar with Smith charts, right? So do you all feel comfortable with Smith charts now? Yes? No, sort of, maybe. I think some of you want to say no, but have a look at it. Have a look at the notes. I mean, what I've done in this particular case is I've actually, Poser does a terrible job of explaining Smith charts, right? So what I've done is I've given you some more examples so you can actually, go through a step-by-step process in knowing how to use the Smith chart in order to be able to solve some of these problems. Now, in this lecture, let's start talking about designing matching networks. All right. And essentially, when we say that we want to design matching networks, essentially what we're saying is we want to connect two circuits or two components together in such a way that we get maximum transfer of energy between the two circuits. And the reason that we do that is, of course, maximum power transfer, but also if you do that, for example, if you have a very weak signal and, for example, you had, your antenna connected up to your TV, or the input port of your TV, what you want is all the power that the antenna is actually has been able to capture. You want it to be able to put it into the input port of the of your television in order to be able to amplify it and get a good quality picture. Right. Now, the number of times I've heard people incorrectly apply, this design of matching networks is phenomenal, right? So I guess we'll talk about the maximum power transfer theorem, right? Which is what you hear, people regurgitate time and time again, which is, hey, if you've got a load and you want to match it, you conjugate match it, right, which is, so if you had 50 ohms, connect 50 ohms to it, or if you had 50 plus j ohm plus 10 j ohms, you want 50 minus 10 j ohms, right? That's the maximum power transfer theorem. But the thing there is that that theorem only applies when the source impedance is fixed. You've got no ability to change it, and your network is passive. Right? And the reason why I'm trying to emphasize that is if you're designing a power amplifier, right, don't necessarily match everything, because that's not necessarily when you'll get the maximum gain. And what we'll do is we'll start talking about, in the next lecture, we'll start talking about maximum transducer gain and how to design power amplifiers, right? But the important thing here is if you've got a passive network and the source impedance is fixed, yes, impedance match. But if you don't, if you've got active components and or the source impedance isn't the source impedance isn't fixed, it's not necessarily the best thing to do. Because think about it, what you're saying is if I source match or impedance match, if I've got 50 ohms here and I've got 50 ohms on my load, I'm only delivering 50% of my power to the load. Right? So imagine, you've got a huge generator. I don't know if it's still switched on your lawn or whatever. It was a coal-fired plant, right, which would generate, most of the power for Victoria. Imagine if you conjugate matched, it would mean, the rest of Victoria was using 10 megawatts, or probably a gigawatt these days. It means I would have wasted a gigawatt at the generator, right, if I was conjugate matching. You don't want to do that. You don't want to be losing 50% of your power, right? But you do that if the source impedance is fixed. Like, for example, you had an antenna and you wanted to get the maximum power, you can't really do anything better. And I'll show you why that's the case. If you've got a passive circuit, you can't really do anything better. And just to reiterate, we had the maximum power transfer theorem. That's what we're going to talk about. And, just for everyone's benefit, I'll reiterate it. It's the maximum power transfer theorem states that the maximum power that can be delivered to a load occurs when the load impedance is the complex conjugate of the source impedance. Right? And essentially, here, I'm going to go through some mathematics, very quickly in order to show you if I've got a source, and this source has got a known fixed source impedance, that, essentially the optimal load impedance is the complex conjugate. So let's prove it. So, the voltage across the load is just VL times IL, which is Ohm's law. We know that the current in steady state, in this particular case, is just Vs Zs on ZL. And we know that the power of that is transferred is just a half the real part of V times I. And you can rewrite all of that in such a way that you now have the average power is the voltage, the magnitude of the voltage of the generator squared, RL on RS plus RL squared plus XS plus XL all squared, right? I've done nothing magic here. I've just rewritten the load and source impedances in terms of the real and imaginary components, and worked out what the power is going to be that is going to be dissipated across that load. Now, all I'm going to do is try to work out a stationary point in order to work out the maximum and minimum, right? So I'm just differentiating. And here what I'm going to do is use a little bit of a trick where that we know that we want the second derivative to be 0, but we also know that one of the conditions that satisfies this is also this first derivative with respect to XL and the second and also the other derivative with respect to RL are both 0. Right? That's also a condition that satisfies this. So once we differentiate, we can actually show that a stationary point occurs when XL equals to minus XS, and therefore we know that the average power that's delivered to the load is Vs squared RL on 2 RS plus RL squared. Now, you can go through and then differentiate this with RL, right, in order to use the second derivative, and what you find is that stationary point occurs also when RL equals RS. So essentially, if you go through the mathematics, all that we've proven is, yes, if you've got a known fixed source impedance, that the maximum power is transferred to the load when the load is the complex conjugate of the source impedance, right? Now, we can go through and work out what the average power is going to be. Anyway, so you can go through the mathematics and convince yourselves that this is actually the case. The 8 comes because I've got you've got RS plus RL. I've got RS plus RS all squared, so it's 2RS squared, so that becomes 4RS squared. So that's where the 8 comes out, right? And the RL equals to RS, so therefore that's why it cancels out and you've only got an RS in the bottom there. But anyway, when you work out the average power onto the load from the relative to the average power that's available from the source, what you convince yourself is you're only getting 50% of the power. So 50% expended or lost in the generator source impedance, and the other 50% is going to your load. So you don't want to really do that unless, if you've got flexibility in order to choose your source impedance, you choose it appropriately. If you don't, like for example, you had an antenna, well, you can't do any better than conjugate matching. Okay. Now, what I'm going to talk about is, well, how do we match? And essentially what I'm doing here is talking about something called L networks. And the point is here I'm going to be looking at matching, in the first instance, using lumped components. So my question is, can we use the Smith chart if we've got lumped components? Yes. Yes. Now, what I'm also I'm also showing two circuits, right? So here I'm trying to match the characteristic impedance of this line to the load, and I've drawn two circuit configurations, right? In the first case, I've got a shunt susceptance at some distance from the from the load. In this particular case, I can even just, if they're lumped, I can just have it across the load, immediately across the load, or it can be some distance. And then I've got a series susceptance, whereas in circuit B, I've got series and then shunt. Right? So there's two potential options. If I can add a series and a shunt element, there are two options that I can write that circuit or draw that circuit. Or two possible circuits that I can use, right? If I'm going to be using lossless reactive components. Right, now, the question is, when would you use each one of these, right? In order to do the matching. In most cases, there isn't a reason why you'd prefer one over the other. The reason why I'm giving you some rules now is that if you choose one over the other, you're always guaranteed a solution, because there could be situations where, for example, if you had a particular load impedance and you chose a shunt series rather than a series shunt, there might not be any capacitors and inductors which will give you a match, right? Whereas if you use the following rule, if you said, well, if my real part to my load is greater than the characteristic impedance of a line, and I use this configuration of circuit, I'm always guaranteed a solution.
And likewise, if the real impedance is less than the characteristic impedance, and I use this type of circuit, I'm always guaranteed a solution. So that's the motivation, right? There's two types of circuits. You can configure this if you're trying to do impedance match using lossless components. There are two options, right? If you're using, just using series shunt or shunt series, there are two options. And if you want to save yourself a little bit of pain, what you can actually do is to say, well, if I know my real component is greater than my characteristic impedance, if I use circuit A, there is always two sets of either capacitors or inductors, or a ratio or capacitors and inductors, which actually allow me to get a perfect match. And if the real impedance is less than Z0, this circuit always guarantees me a solution. That's the only reason I'm choosing it, right? Does that make sense? Yes?
If you use more than just two components.
Yeah, but that's different.
Okay.
All right. If I said to you, you can only use two components, and you say to me, well, which circuit should I use? You can say, well, you can use either, but there might not be real value. There might not be a capacitor and an inductor, or capacitor and inductive solutions that give you a solution. But if you chose them in this particular way, using this criteria, you're always guaranteed a solution. That's all I'm saying. So rather than trying to solve it and then find, I didn't get a solution, damn, I've got to start again. If you start off using that information, then you know that you're going to have a solution, right? So, RL greater than Z0, use configuration A. RL less than Z0, use configuration B. Now, if you want to go through the proof, you can look at page 283 of POSA to go through the proof. For all of you that are so inclined, go right ahead. It's very interesting, and I would recommend it, but I just didn't want to go through it in this particular lecture. But it explains to you why there's always a solution if you choose it in this particular manner. I'm saying I'm putting some of you to sleep. I'm just worried. This is exciting stuff. It's not boring stuff. Come on. All right, so let's look at some of these rules. If we're designing, these circuits and how to do the impedance match. And again, we can use, how do you call it? We can always use a Smith chart. So the rules that I would recommend that you use so that you can always get a solution is, always use, a Smith chart, unless you're mathematically inclined. I usually like doing the mathematics, but because I'm terrible at drawing. But if you want a very fast solution, the Smith chart's excellent. So I would say use the Smith chart. Now, the other rule that's important, even for lumped components, is, because it causes some confusion because it's a lumped component. People say, what does it all mean? Moving towards a generator, moving towards a load. When do I do what? The second rule I would say is always start at the load and move towards the generator. Right? And the third rule is always move on constant resistance or constant conductance circles, right? And try to move towards the center of the Smith chart. Why am I suggesting this? Yes?
Because we know that when we reach the center, then we've got implementation.
Yes, and we're also adding capacitors or inductors in this particular case, right? That's what we're only using lossless components, so therefore we're only adding J's, right? So don't try to move, off the constant R or constant G. And you're right. If you do that and you're always on a constant R or a constant G circle, it also means that there's always a path for you to get to a perfect match. Now, the other thing that it's worthwhile remembering is if you're adding something in series, you're moving on constant R circles or constant resistance circles, and if you're adding things in shunt, you're moving on constant G or constant conductance circles. No big deal. I mean, that's obvious, right? But I'm just trying to re-emphasize that that's the case. Now, the other bit of information that I think is useful, and because it always confuses me, right? So therefore, that's why I've written it down. So therefore, it doesn't, So hopefully, you remember it as a rule. So then you don't make the same mistake that I usually make. So if you're on a constant resistance circle, if you're moving clockwise or towards the generator, you're adding a series inductance, right? And if you're moving anti-clockwise, you're adding a series capacitance, right? If you think about it, if I'm going up, I'm adding inductance. I'm going down, at least if I'm in series, I'm adding capacitance, right? That's where that comes from. And likewise, the opposite when you're on G circles, right, on admittance one, because if you're 1 on J omega C becomes, omega C, right? And likewise, 1 on J omega L becomes 1 on J omega L, which becomes minus J omega L on omega L, right? That's the reason for these rules. Now let's try to put it into practice. And which is as follows, right? I want you to design a lumped element matching network at 1 gigahertz that transforms this load to 50 ohms. Okay, so the first thing is we would do is, you can decide which step 1 or step 2 can be. You can decide whichever one step is the first step. But okay, using our rules, since ZL is less than 50 ohms, I would use which type of circuit? Right, so I would have a series component first and then my shunt element. Right? Okay. So we know the form of the circle that we're going to use. And so the first thing that we will do is we've got ZL equals 10 plus 10J omega, Z0 equals to 50. So let's work out what ZL is and put it onto the Smith chart. Okay, so we know ZL is here, and we want to add some reactive component to it. Now, in order to work out what the reactive component is going to be, what I suggest that you do is you also work out, because here you're going to add some reactive component, and you don't really know what reactive component you should add, right? So now you're going to ask me, what are the potential reactive components that I can add in order to allow me to add a shunt so that I can get to the origin? And the best way of being able to do that, or the only way to be able to do that, is to then draw the voltage standing wave ratio curve for 1 plus J beta, which is the unit susceptance circle. Rather than going here where you've got Z equals 1 plus J beta, I'm asking you to draw the line Y equals 1 plus J beta. Right? Sorry, the circle. So essentially what we do is we're essentially drawing the constant, this circle, which is 1 on, this circle, which is 1 plus J beta, we're actually transferring it. So therefore what we're doing is, we're flipping it around. So the way that you flip it around is essentially you grab this circle, you work out half the radius, and then start at that point, draw the circle. And that gives you the line 1 plus J beta. Right? So that's your 1 plus J beta susceptance circle. All right, so as you can see here, there's 2 points of intersection, right? What does that mean? There's potentially 2 points where I can choose jx, right? Which will allow me, if I drew, for example, if I drew the first one, I go to this point, I flip around in order to get to susceptance, and then, because remember, I'm still in the resistance plane here. If I know what I want my susceptance, one on the susceptance to be, I get to this point, flip around, and then that's the susceptance that will give me what I need to get to the origin, or I can go essentially, put a much larger value and flip all the way around, and I get the second point, which will lead me up here, and then I'll move along this line to get to the origin. So I've got 2 choices, and it really, part of it, is also, do you have what do you have available to you in order to do the match, right? In this particular case, we didn't actually have any constraints. So I said, well, do whatever you like. So the easiest thing is go to the first point at which we've got some, where we've added some elements, some reactive element which gets us to the circle of constant impedance, 1 plus j beta impedance. Get to that point, now we've got that particular impedance. That actually tells me how much I've got to add, which is 0.3, and I'm going to 0.4, so therefore that actually allows me to work out that I've actually just got to add this much inductance, or if I was adding, go all the way around, or if I'm going down, I can add this much capacitance, right? So it depends on what values of components that you have available to you in order to do the matching. And in this particular case, I'm saying, well, just the easiest thing is just to add the inductance, because it just gets us to this first intersection point. All right. So we get to this point, and usually, as a rule of thumb, what we do is we usually choose the smallest values. That's probably why there's also an advantage in actually hitting this point rather than choosing a much larger capacitor. Anyway, so we move to this point. We actually, because we're going to add now, we want to be adding a shunt element. So we've got to convert the impedance into admittance. So we flip through the origin till we get to this point, right? And now we've got to work out what susceptance element do I need to add in order to get to the origin, right? Because I want to get to the origin to get a perfect match. Right, so therefore, if we look at this, we say, in this particular case, our susceptance is 1 plus 2 minus 2j, and then you can work out, well, what susceptance do I need to add? Right, so we go through that, and we know that we're going to be moving in the clockwise direction for susceptances, so we know it's a capacitance. So we know that j omega c is equal to 2, because we're at minus 2 and we want to add positive 2. If we're normalizing, it's 0.2, so j omega c equals 2 times 0.2, which is 1 on 50. And once we've got this, we know what the frequency is. We can always work out what the capacitance is, right? So we know that the capacitance that we need to add is 6.37 puffs or picofarads. Does that make sense, or is it? I think I've. Yeah, you got to do it yourself. But I've done everything step by step, right? So go through it. So really, I guess the only step that I haven't explained previously is that because we're going to be adding susceptances, sorry, we're going to be adding shunt, something in parallel, or shunt elements. The easiest way in order to be able to know what the value is going to be in order to be able to get a unique solution is draw the circle 1 plus j beta for y, and the location, the two locations at which you add a series element, or the 2 points at which it intersects are the two possible solutions. Does that make sense? If we went anywhere else, there's no guarantee that we'll end up on the 1 plus j b z equals 1 plus jb line, right? So the only way that we can guarantee that we're going to get a solution that only requires us to add a shunt capacitor or a shunt inductor is if it intersects with y equals 1 plus j beta. That's the only reason why I've drawn that line, of that circle, I should say. All right. Not getting feedback. I'm just worried. Everyone understands that? Everyone appreciates that? Everyone's bored out of their minds or something? Or I'm just trying to... All right. Okay. Does someone want to explain it to me? Maybe one of you goes, well, okay, Stan, this is what we're doing. Who wants to explain to me the steps that I've undertaken? Anyone brave enough? Everyone's looking down, or anyone game? Put up your hand, come on. No? All right. Should I repeat it? What don't you understand? Perfect. All right, so you don't understand how to draw that? Okay. You don't understand how to draw it or why to draw it? Why we're drawing it. Okay. Okay. What we want is we want to get to a line in susceptance, which is essentially we want the impedance to be Z equals 1 plus, we want it to be equal to 1, right? We want to end up Z equals 1, right? Correct? In order to do the impedance match. Okay. Now we know that if we're on impedance, we can work out susceptance, or sorry, admittance, I should say admittance, by going through the origin, right? So we just flipped through the origin. Okay. But we're only going to use imaginary components, right? We've only got imaginary components, inductors and capacitors, because we said we're going to build a lossless circuit. How can we guarantee that? I mean, what do we have available to us in order to ensure that that's the case? So what we want is we want a situation where we end up on the line Z or Y equals 1 plus JB, right? Or something like that, right? So how can we do that? Well, the only time that we're guaranteed that is if we draw the line of constant of admittance being 1 on plus JB, right? So therefore, once we reflect, we know that we're going to end up on that particular curve. All right. So how do we draw 1 on JB? Well, 1 on JB, it's really simple, right? So this is the line Z equals 1 plus JB. 1 plus JB. So this is a circle of Z equals 1 plus JB, right? This circle here. All right. And we know Z equals infinity maps to Z equals Y equals 0. And we also know, for example, you know, and the only thing that I do in order to work this out is I just say, well, what's the radius of this circle? You know, work out half of it. Probably the easiest thing is just work out half of it.